Hi everyone, I'm JJ, and welcome to RadioTech Academy. I've been working in medical imaging for over 20 years. During this time, I've installed and repaired many X-ray systems and trained others to use and truly understand them. Over the years, I've helped hospitals, engineers, and students discover how imaging devices really work, from the inside out. Today, we're going to explore the fascinating world of X-rays. These invisible rays can reveal bones and tissues without ever opening the body. Imagine being able to see inside the human body with an invisible beam, and finally understand what's happening beneath the skin. Let's take a step back in time to where it all began. The story of X-rays starts in 1895 with a German physicist named Wilhelm Conrad Roentgen. While experimenting with cathode rays, he noticed a strange glow on a nearby screen, a glow that appeared even when objects blocked the path of light. Curious, Roentgen placed his hand between the tube and the screen, and what he saw was incredible, the shadow of his own bones. A few days later, he repeated the experiment with his wife's hand, capturing the very first X-ray photograph in history. When she saw her own bones, she reportedly said, "I have seen my death." That image, the bones of Bertha Roentgen's hand, became one of the most iconic scientific photographs ever taken. Soon, doctors and scientists around the world were fascinated. Within just a few months, hospitals began using X-rays to examine broken bones and locate foreign objects inside the body, without surgery. But the story didn't stop there. Around the same time, Marie and Pierre Curie were studying radioactive elements, discovering polonium and radium, which emitted their own mysterious rays. Their work helped scientists understand how energy and matter interact at the atomic level, and how these rays could be used for both medicine and research. In 1901, Wilhelm Roentgen received the first ever Nobel Prize in Physics for his discovery of X-rays, an achievement that forever changed modern science and medicine. From that moment on, radiology was born. Over the years, X-ray technology evolved, from simple glass tubes to powerful digital imaging systems we use today in hospitals and laboratories. And now, every time we take an X-ray, we're building on more than a century of science, discovery, and human curiosity. So let's continue this journey and see what really happens inside an X-ray tube. Let's start by looking at the atom. It has a nucleus made of protons and neutrons, and electrons orbiting around it. Electrons move in defined energy levels, called K, L, M, N shells. Each shell has a specific capacity. K equals 2, L equals 8, M equals 18, N equals 32. When an inner electron, for example in the K shell, is removed, a vacancy is created. Electrons from outer shells move down to fill the vacancy. The energy difference between these shells is released, and that energy is called a characteristic X-ray. In metals like tungsten, atoms are connected by covalent bonds. Each atom shares some of its electrons with neighbors. Some electrons remain free, moving easily through the metal, like waves in an electron sea. These free electrons allow the filament current to flow easily and help X-rays to be produced efficiently. The filament is a metal wire located in the cathode. When electricity passes through it, it heats up and releases electrons. These electrons later travel to the anode and produce X-rays. The size of the filament greatly affects the final image. Small filament. Electrons hit a tiny spot on the anode. This creates a small, focused X-ray point, making the image very sharp and detailed, like drawing with a fine pen. Large filament. Electrons hit a larger area on the anode. This makes the image softer and wider, but heat spreads over a bigger surface, and the tube can operate longer without overheating. In simple terms, the filament size is like using a fine pen or a broad pen. One gives sharp detail. The other manages heat better and extends the tube's life. After being released, electrons must accelerate toward the anode. This acceleration is driven by a high DC voltage generated by the X-ray generator, typically between 20 and 150 kilovolts. When electrons hit the anode, their kinetic energy converts into two types of X-rays: deceleration radiation. Electrons deflect near the nucleus, releasing energy as X-rays. Characteristic X-ray: an outer electron fills an inner electron vacancy, releasing energy, as a characteristic X-ray. These two types of X-rays combine to form the final X-ray beam exiting the tube. Let's take a detailed look at the focal spot, filament size, and the Heal effect in X-ray imaging. The filament is the metal wire in the cathode that releases electrons when heated. Its size determines the number of electrons that can be emitted. A small filament releases electrons from a limited area requiring less current, while a large filament releases electrons over a bigger area, allowing higher current and longer exposure. Choosing the filament affects tube heating, power capacity, and the overall efficiency of X-ray production. The focal spot is the area on the anode where electrons actually hit. A small focal spot concentrates the electrons in a tiny area. This produces a narrow, well-defined X-ray beam, interacting with the object in a more precise way. A large focal spot spreads electrons over a wider area, creating a broader X-ray beam that covers larger portions of the object, but with less concentrated energy. It is important to note that the focal spot and filament size are related, but separate concepts. The filament size controls how many electrons are released and how the tube handles heat, while the focal spot determines how the X-ray beam interacts with the object. Now let's consider the Heal effect. X-ray intensity is stronger on the side of the anode near the filament and weaker on the opposite side. This can be useful when imaging thicker body parts because the stronger X-rays can be directed toward the thicker sections. However, it can also create uneven brightness in the image if not considered. In summary, choosing a small filament and small focal spot gives precise, concentrated X-rays suitable for small structures, while a large filament and large focal spot allows higher power, better heat management, and imaging of larger objects with a broader beam. Understanding the combination of filament size, focal spot, and Heal effect helps control image quality, exposure, and safety. Now let's take a closer look at the types of anodes used in X-ray tubes and why they are important. There are two main types of anodes: stationary and rotating. A stationary anode has a very simple design and costs less to make. It is usually used in machines that work with a low amount of current, such as small dental X-ray units. However, there is one big disadvantage. When electrons hit the same area again and again, the heat cannot spread out. That heat builds up and can eventually damage the anode surface. Because of this, stationary anodes are only used for short exposures or low-power imaging. The rotating anode, on the other hand, spins quickly during operation. This rotation spreads. The electron impacts over a much larger area. That means the heat can be distributed more evenly, and the anode stays cooler for longer. As a result, rotating anodes can handle higher exposure times and produce a stronger X-ray output. They are used in modern systems such as CT radiology and fluoroscopy machines, where high performance is needed. Of course, rotating anodes are more complicated. They have motors and bearings that make them more expensive, and those parts can wear out over time. So, while they provide better results, they also need more maintenance and care. Inside the X-ray tube, there is a complete vacuum. The vacuum allows electrons to move freely from the filament to the anode without bumping into air molecules. If even a small amount of air enters the tube, the electrons will collide with the gas and lose energy. That reduces the efficiency of X-ray production and can even damage the tube. Finally, Outside the tube, there is often cooling oil. This oil helps absorb the extra heat and keeps the temperature stable during operation. To sum up, stationary anodes are simple and low cost, but they can overheat easily. Rotating anodes are powerful and efficient, but they are more expensive and require more maintenance. Both types depend on the vacuum and cooling system to work safely and effectively. Sometimes in an X-ray tube, something unexpected can happen. A small electrical discharge known as an arc. An arc occurs when the vacuum inside the tube is no longer perfect. If air or moisture enters, the electrons can strike the gas molecules instead of the anode. This creates a bright flash or spark, and you might even hear a short cracking sound. When this happens, the current does not follow its normal path between the cathode and anode. Instead, it jumps across the gas, creating a short circuit inside the tube that can reduce the X-ray output or even damage the internal components. Arcing usually means that the vacuum seal has been weakened or that the anode and filament surfaces have become contaminated over time. That's why maintaining the vacuum level is critical for the safe operation of the tube. To prevent arcs, modern systems use stable high-voltage supplies and carefully sealed glass or metal housings. Technicians also monitor the vacuum and replace aging tubes before they fail. So even though an arc is small, it's a serious warning sign that the tube needs attention or replacement. When X-rays pass through the human body, not all of them travel the same way. Different tissues absorb X-rays differently, depending on their density. Bones are dense and absorb most of the radiation. That's why they appear bright or white on an X-ray image. Soft tissues, such as muscles or organs, allow more X-rays to pass through. They appear darker on the image because less radiation is absorbed. Typically, about 70 to 90% of the X-rays are absorbed by bone, while the rest either pass through or scatter in other directions. This difference in absorption creates the contrast we see in medical images, helping doctors identify fractures, tumors, or hidden structures inside the body. Beyond medicine, X-rays are also used in industrial inspection, security scanners, and scientific research, where they help us look inside materials without damaging them. Now let's bring everything together. The filament heats up and releases electrons. Those electrons accelerate toward the anode under a very high voltage. When they strike the anode, they generate two kinds of X-rays: deceleration radiation and characteristic radiation. The deceleration radiation come from the sudden deceleration of electrons, while the characteristic rays are produced when electrons move between atomic shells. The size of the focal spot, the type of anode, and the Heal effect all influence the sharpness and intensity of the final X-ray beam. Finally, the X-rays pass through the patient, and the different tissues absorb them differently, creating the image we see on a film or digital detector. So next time you see an X-ray image, remember, behind that picture lies a fascinating process of physics, electrons, and energy transformation. This is the science behind the invisible light that lets us see inside the human body. And that's the end of today's lesson. I hope you enjoyed learning about the science behind X-rays and discovered something new today. If you liked this video, please subscribe to our YouTube channel, leave a comment, and share your thoughts with us. Your support gives us the energy to create more educational videos about radiology and the amazing world of medical imaging. Thank you for watching, and see you in the next video.